Unlock the potential of artificial intelligence. Welcome to Deep Learning and Generative AI.
All right, welcome. This is Week 8, Part 1 of our dive into deep representation learning. Today, we are getting into something really foundational, a super powerful tool in unsupervised learning, the classical and regularized autoencoders.
So let's kick things off with a huge challenge we face all the time. The world is just filled with this messy, high-dimensional data. I mean, think about a single high-resolution image. That's millions of dimensions, one for every pixel value. It seems totally overwhelming. But there's this really beautiful idea that helps us cut through the noise. It's called the manifold hypothesis. The theory is that all that complex data isn't just randomly splattered everywhere. Instead, it actually clusters together on a much simpler, lower dimensional surface, a manifold, that's just kind of twisted up inside that high-dimensional space. Our job isn't just to compress the data, it's to find a hidden surface and learn its true coordinate system.
Okay, so if the goal is to learn this hidden manifold, how do we actually do it? What's the right tool for the job? Well, that brings us to the star of today's show, the autoencoder. Let's break down its blueprint. Let's start with the simplest version you can possibly imagine, the linear autoencoder. It's just a basic neural network. It takes some inputs, squishes them down into a much smaller set of hidden units, you see Z1 and Z2 here, and then it tries to rebuild the original inputs from that squished version. The key word here is linear. Because it's only using simple linear math, it's been proven that this network ends up learning to do the exact same thing as a classic statistical technique called principal component analysis, or PCA. It's basically just finding the best flat surface to represent all the data points. But here's the thing, real-world data manifolds are almost never flat, right? They're all curved and complex and tangled up. And to capture that, we need to go deeper. We need deep autoencoders. This architecture has three key parts. First, you've got the encoder, which is a stack of nonlinear layers that maps the input down to this simplified, compressed code. Second, the bottleneck. That's that really tight middle layer that forces the network to only keep the most essential features. And finally, the decoder, which takes that tiny code and tries its best to reconstruct the original input, basically learning how to unwarp that hidden manifold. And you have to understand, this bottleneck is everything. By deliberately creating a layer that has way fewer dimensions than the input, we are forcing the network into a corner. It literally can't just mindlessly copy the data through. It has to figure out a compressed representation. It has to decide what information is absolutely vital and what's just noise that it can throw away. This constraint is the engine that drives all the learning. Okay, so this all sounds amazing. We have this powerful tool that can dig into complex data and find the simple hidden structure. But, and this is a big but, this power comes with a pretty serious weakness. There's a way this whole elegant system can just completely fall apart, and that's the memorization problem. So let's think about this for a second. What happens if we get a little too generous with our network? You know, what if we make it really deep, give it a ton of capacity? Or maybe we make that bottleneck layer not really a bottleneck at all. What's the worst that could possibly happen? Well, what happens is something called the identity trap. If the network is powerful enough, it's going to find the laziest possible solution. It'll just learn the identity function, which means it just copies the input directly to the output. And you know what? Your reconstruction error will be 0. It'll look perfect on paper, but the model has learned absolutely nothing. It's just pure memorization. The latent space is just a jumbled copy of the input, and we have totally failed to learn any useful features. So clearly, just relying on a small bottleneck isn't enough. We need a smarter, more robust way to stop the model from cheating like this. We have to force it to learn something meaningful, even if it has enough power to just memorize everything. And this leads us to some really ingenious fixes. The fix is a concept called regularization. Take a look at the equation. Instead of just trying to minimize the reconstruction error, we add a second term to our loss function, a penalty for being too complex. So now, the model is trying to do two things at once. It wants to create a perfect reconstruction, sure, but it's also being punished if its internal representation gets too complicated. It's this trade-off, this tug-of-war, that stops it from taking the easy way out and forces it to find a simple, general structure. And this core idea of adding a penalty has led to a few really clever strategies. The three main ones you'll see are sparse autoencoders, which basically force most of the hidden neurons to just shut off. Then there are denoising autoencoders, which we're going to dive into in just a second. And finally, contractive autoencoders, which encourage the model to ignore tiny irrelevant changes in the input. Now, of all those methods, there is one that is just so intuitive, and it's turned out to be incredibly powerful. We're going to really focus on this idea of forcing the model to learn by having it rebuild things from noise. And this is how a denoising autoencoder, or DAE, works. The process is so simple, but it's just brilliant. You start with your clean input, X. Then you deliberately corrupt it. You add some random noise to get this damaged version, X tilde. Now you feed that corrupted input into the autoencoder. But here's the twist. The model's goal isn't to reconstruct the noisy thing you gave it. Its goal is to reconstruct the original, clean version. The error is measured between the model's output and that pristine original input. Just stop and think about what this task actually requires from the model. To reliably remove all that random corruption, it can't just be a dumb copy machine anymore. It is absolutely forced to learn the real statistical structure of the data. It has to build an implicit understanding of what a valid data point is supposed to look like, so it can recognize the junk and fix it. This all leads to a really beautiful, geometric way of thinking about it. What the denoising autoencoder is really learning is a vector field. Each one of those little gray arrows is a direction. So if you drop a corrupted data point anywhere off the path, the model has learned which way to push it to get it back onto that high-density data manifold. It's basically learning the energy landscape of your data, and it always knows how to move downhill towards the most likely, most stable configurations. And this is not just some old academic idea, okay? This same core principle is being used in state-of-the-art models today, like the masked autoencoder. And it takes this whole denoising idea to the absolute extreme. We're not just adding a little noise. We are completely masking out huge chunks of an image, sometimes up to 75%. And the model's job is to reconstruct the entire cheetah from just those few little patches it can see. Now, to do that, it can't just look at local textures. It is forced to learn global semantic concepts. It has to learn the idea of what a cheetah is. So, wow, we've covered a lot of ground here, right? We've gone from the simplest linear models all the way to these incredibly powerful regularized versions. Let's do a quick recap of our journey, and then I want to tee up the next big challenge that none of these models can solve. This table kind of sums it all up nicely. You've got your linear and deep autoencoders, which use a physical bottleneck. Then you have the sparse and denoising ones, which use a penalty or a difficult task as their constraints. But do you notice the common thread? Every single one of these models defines a deterministic mapping. For any given input X, there is exactly one output Z in the latent space. And this, it turns out, leads to a major problem. And that problem is what we call the generative gap. In this picture of the latent space, the model has learned where the real data is supposed to live. It's along those bright, high-density ribbons. But what about all that empty, black space in between? Because the decoder is totally deterministic, and it's only ever seen points on that manifold, if we were to pick a random point from one of those gaps and ask it to decode, it has no idea what to do. It just spits out noise, total garbage. So these models are fantastic for representation, but they are terrible at generation. Which leaves us with a final, really provocative question. We've totally mastered the art of learning representations and finding structure in data. But how do we bridge that gap? How do we build a model that can not only represent the data it's already seen, but can actually generate completely new, totally realistic samples from scratch? That is the question we're going to answer in part 2, when we explore variational autoencoders. I'll see you then.